Hello again. There are 118 elements currently on the periodic table. There are about 98 different elements in nature. However, the world would be dull and lifeless with only 98 substances. Fortunately, elements combine with each other to form compounds. The richness of our environment is due to a huge collection of compounds, just as combination of only 26 letters in English alphabet allow for an almost limitless number of words. So combinations of the 98 naturally occurring elements allow an almost limitless number of compounds. And there is usually little about compound to suggest that the element is present in it. Elements lose their own peculiar properties when they enter into combination with other elements. But what holds atoms together to form compounds such as water and salt? We have learned that atoms have electrons and that these electrons participate in bonding one atom to another. Today we will discuss bonding mechanisms and the important types of chemical bonds, ionic bonds and covalent bonds. But before we dive into understanding the key terms, let's make a list of them. Perhaps you are already familiar with some of these. Are you? Remember, in lesson number 2, we learned that pure substances could be divided into elements and compounds. We could further subdivide elements and compounds according to the basic units that compose them. Elements may be either atomic or molecular. Compounds can be either molecular or ionic. As you have learned, atoms are electrically neutral, with the total negative charge of all its electrons matching and cancelling the total positive charge of all the protons in the nucleus. When an atom loses or gains electrons, the balance of charges is upset and the atom becomes an ion, ioni. An ion is an atom or group of atoms that has a net positive or negative charge. Cations, cationit, are positively charged ions. Cations are formed when a metal loses electrons. Anions, anionit, are negatively charged ions. Anions are formed when a nonmetal gains electrons. Now I have blurred the transition metals. Let us just forget them and discuss main group metals, those that are bright blue. The charged on main group ions can be predicted from the position in the periodic table. A main group metal tends to lose electrons, forming a cation with the same number of electrons as the nearest noble gas. If we look at the groups 1 and 2, the nearest noble gas is the one that precedes the element, is at the end of previous period. Those main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So, an atom of an alkali metal group 1 loses one electron and forms a cation with a 1 plus charge. And an alkaline earth metal in group 2 loses 2 electrons and forms a cation with a 2 plus charge. On the other side of the table, the group 17 nonmetals, the halogens, have 7 valence electrons and they form 1 minus ions. For example, when chlorine gains an electron, it ends up with the same electron arrangement as its neighbor, noble gas argon. Ionic compounds, ioniyhdisteet, are composed of cations and anions bound together by ionic bonds. An ionic bond, ionisidos, is formed when one of the atoms can donate electrons to achieve the noble gas electron configuration, and the other atom needs electrons to achieve the noble gas electron configuration. So, ionic bond is the chemical bond formed by the transfer of electrons from metal atoms to non-metal atoms. The best known ionic compound is common table salt, ruokasuola, or sodium chloride, natrium chloride. The atomic number of sodium is 11. Sodium has only 1 electron in its outermost shell. Sodium would become stable if it could lose that electron and attain the configuration of neon. So, sodium atom would donate 1 electron. On the other side, the atomic number of chlorine is 17. Chlorine atom has 7 electrons in the outermost shell and needs 1 more electron to achieve noble gas configuration. So a chlorine atom takes 1 electron from sodium atom. With 1 electron stripped off, sodium with its 11 protons and only 10 electrons now has a net 1 plus charge. When an electron is added to chlorine, the 18 electrons produce a net 1 minus charge. The chlorine has become a chloride ion. Sodium ions have positive charge, whereas chloride ions have negative charge. Due to opposite charges, sodium and chloride ions are held together by the electrostatic force of attraction to form sodium chloride, natrium chloride. In sodium chloride, sodium and chloride ions exist in 3-dimensional alternating array. Because ionic bonds are not directional, no one sodium ion pairs with a specific chloride ion. Rather, as you can see from this figure, any one Na plus cation is surrounded by Cl minus anions and vice versa. Sodium chloride's formula unit is the simplest charge-neutral collection of ions. The formula unit tells us that sodium chloride is composed of sodium and chloride ions in a 1:1 ratio, while common table salt is sodium chloride. Salts can more broadly be defined as neutral ionic compounds composed of related numbers of cations and anions, so that the product is electrically neutral without a net charge. A substance can conduct electricity if it contains charged particles and if these particles are free to move from place to place. The ionic compounds, when dissolved in water, undergo an important change. They fall apart or dissociate into ions. For example, sodium chloride dissociates into the ions Na+ and Cl-. Electrically, this solution is neutral, but if an electric potential is applied to this solution, the cations and anions of the solution are drawn to different electrodes. Positively charged cations travel to the negative cathode, and negatively charged anions travel to the positive anode during electrolysis. The movement of anions and cations in opposite directions within the solution amounts to a current. So, as salts dissociate when dissolved in water, the resulting solution is electrically conducting. We can say that soluble salts are electrolytes. So, an electrolyte means a substance that produces an electrically conducting solution. Sugar, on the other hand, is not an ionic compound, so it does not dissociate, and its solution is not a conductor of the electric current. Covalent compounds do not exhibit any electrical conductivity, either in pure form or when dissolved in water. Notice that even ionic compounds cannot conduct electricity when solid, as the ions are held in fixed positions and cannot move. Ionic compounds conduct electricity when they are molten or dissolved in water. Binary ionic compounds are ionic compounds that contain only two types of elements. They are named by writing the name of the cation first, followed by the name of the anion. The cation retains the same name as the element. The anion's name is similar to the elemental name, but the ending of the name has been removed and replaced with "id", suomeksi idi. A molecule, molekyyli, consists of a group of two or more atoms joined together by covalent bonds. Whereas ionic compounds are usually formed when a metal and non-metal combine, molecular compounds are usually formed by a combination of non-metals. When a non-metal bonds with another non-metal, neither atom transfers its electron to the other. Instead, some electrons are shared between the two bonding atoms. Shared electrons in a covalent chemical bond hold the bonding atoms together by attracting the positively charged nuclei of the bonding atoms. The Octet Rule is a chemical rule of thumb that a stable arrangement is attained when the atom is surrounded by 8 electrons in its valence shell. Main group elements tend to bond in such a way that each atom gets the same electron configuration as a noble gas. This octet can be made up by own electrons and some electrons which are shared. Thus, an atom continues to form bonds until an octet of electrons is made. A shared pair of electrons contributes to an octet on both atoms. The octet rule helps visualize how atoms combine by looking at how they share electrons. A simple example is the structure of a water molecule. Oxygen, with its 6 outermost electrons, can accommodate 2 more electrons to complete its outermost shell, which can hold a maximum of 8 electrons. A hydrogen atom can provide 1 electron and can complete its own outermost shell, the only one it has, by acquiring 1 more electron. Remember that first innermost layer can accommodate only 2 electrons. Sharing can be complete, provided 2 hydrogen atoms are content to share 2 electrons with oxygen. The hydrogen atoms each get a share in 2 electrons. And the oxygen atom gets a share in 8 electrons. Both oxygen and hydrogen now have complete outer valence shells. Carbon is remarkable for the very large number of compounds which it forms with the other elements, especially with hydrogen. Methane, methane, is one of the most important of these hydrocarbons, hiilivedyt. As we just saw, hydrogen as first row element follows a duet rule. It forms stable molecules where it shares 2 electrons. The second row nonmetals, carbon, nitrogen, oxygen and fluorine, always obey the octet rule in stable molecules. That's why methane has 1 atom of carbon and 4 atoms of hydrogen. The carbon atom, central to the methane molecule, has 4 valence electrons and thus needs 4 more electrons from 4 hydrogen atoms to complete its octet. Molecules can be represented in several different ways. The simplest method is the molecular formula. Since the molecule consists of a definite number of atoms, it is very convenient to represent the composition of a molecular compound by using the symbols for the elements to indicate the kind of the atoms which constitute the molecule and subscripts to indicate the numbers of atoms. The formula for methane tells us that each molecule contains 1 atom of carbon and 4 atoms of hydrogen. A molecular formula simply counts the numbers of each sort of atom present in the molecule, but tells you nothing about the way they are joined together. The structural formula for a compound gives the same information as its molecular formula, but also shows how the atoms are connected in the molecule. The structural formula for methane contains symbols for 1 C atom and 4 H atoms, indicating the number of atoms in the molecule, the lines, these lines, represent covalent bonds that hold the atoms together. Notice that the way the methane is drawn bears no resemblance to the actual shape of the molecule. Methane is not flat with 90 degrees bond angles. Ball and stick models are three-dimensional models where atoms are represented by spheres and bonds are represented by sticks between the spheres. Atoms of different chemical elements are usually represented by spheres of different colors. For example, black is usually used to represent carbon and white to represent hydrogen, just like in this picture. Space filling model shows both the relative sizes of the atoms in the molecule and their spatial relationships. The spheres that represent atoms are fused together, and the sides of the sphere represents the size of the actual atom. These models mask the chemical bonds between the atoms and sometimes make it difficult to see the structure of the molecule. Here are some formulas and models for carbon dioxide. In three-dimensional models, oxygen is customarily red. The two lines or two sticks between the carbon and oxygen atoms represent a double bond, which is generally stronger than a single bond represented by a single line. As you can see, the carbon dioxide molecule is formed from one carbon atom and two oxygens. Why? And why are there double bonds? A single bond corresponds to one shared electron pair, while a double bond corresponds to two shared electron pairs. Carbon is in group 14, main group 4, so it has 4 valence electrons. Oxygen is in group 16, main group 6, so it has 6 valence electrons. Remember that the electrons shared by the two atoms in a covalent bond are counted twice. In carbon dioxide, each oxygen shares 4 electrons with the central carbon. Two from the oxygen itself and 2 from the carbon. All 4 of these electrons are counted in both the carbon octet and the oxygen octet. So that both atoms are considered to obey the Octet Rule. Each shared pair of electrons counts as one covalent bond. In triple bond, two atoms share 3 pairs of electrons. Triple bonds are stronger than the equivalent single bonds or double bonds. Electronegativity, elektronegatiivisuus, is the ability of an atom in a molecule to attract shared electrons to itself. Covalent bond between two atoms with unequal electronegativities results in unequal sharing of electrons. A dipole exist when the distribution of electrons within the molecule lacks certain symmetry. The asymmetric distribution of electrons in chemical bonds creates partial charges. For example, because the oxygen atom in the water molecule has a greater electronegativity than the hydrogen atoms, there is some molecular charge distribution, and a water molecule is a dipole. The oxygen side of the molecule is always somewhat negative, and the hydrogen side somewhat positive. The charges of a molecule like water are partial charges, meaning they are smaller than the charge of an electron. Now let's return to this figure that I showed you earlier in this video. It is the polarity of water molecules that enables water to dissolve many ionically bonded substances. Water can dissolve sodium chloride, salt, because the positive part of water molecules attracts the negative chloride ions, and the negative part of water molecules attracts the positive sodium ions. There is one very important distinction between ionic and covalent bonding. Ionic bonding results in huge aggregates of ions, chunks of substance. Covalent bonding commonly results in discrete atomic assemblies. That is, covalent bonding results in individual molecules. It is for this reason that all gases are molecular. There is no such thing as an ionically bonded gas. Even if such a gas was formed, all the ions would immediately clump together as a solid. Also, almost all substances that are liquid at normal temperatures are molecular. As in liquid, the molecules need to be able to move past one another. Now, check what you have learned. Can you define these terms now? Have a great day. Moikka!